Good morning, students. Sage Anandam, coming to the last lecture of our video lecture series of analog and digital communication subject. It is on the QPSK, that is Quadrature Phase Shift Keying. We have discussed earlier what is phase shift keying. Now we'll discuss with the Quadrature Phase Shift Keying. So basically, what is that? This is visible now. Okay. So basically, it is an M-array constant amplitude digital modulation scheme in which the number of bits is 2 and the number of signaling elements are 4. Two successive bits in a bit stream is combined together to form a symbol. Each symbol is then represented by a distinct value of phase shift of the carrier. Each signaling element is represented by 2 bits and is known as the die-bit system. QPSK will have 4 different phase shifts separated by the multiples of 90 degree of the carrier signal. 90 degree of the carrier signal and is represented by VCT is equals to VC cos 2 pi FCT. So mathematically, 4 output phases are possible for a single carrier frequency, that is 0, 0, 0, 1, 1, 0, and 1, 1 dibits. These are the dibits. Sorry. So a single change in the output phase occurs for each of the 2 bits dibit. The rate of change of the output band is equal to 1/2 of the input bit rate. Mathematically, QPSK can be expressed as for a signal 0, 0, it is same as VC cos 2 pi FCT. For 0, 1, it will have a phase shift of pi by 2. For 1, 0, it will have a phase lag of pi by 2. And for 1, 1, it will have a phase lead of again 180 degree. This is the waveform. Students are very confused in these waveforms. This is our binary sequence of the massive signal, which is given as this binary data sequence DT 1 0 1 0 0 0 1 1 1 1 1. So we'll divide this into odd and even. This is our first, then second, then third, fourth, fifth, sixth, and likewise, and mark it as odd and even. So basically, first we take the odd sequence. Odd sequence is 1, 3, 5, 7, and 9. And then 11th bit is not given, so we'll consider with only 9. First bit is 1, then third bit is 1, then fifth bit is 0. So it will continue till fifth bit. Then it has become 0, and at 7th position it has become 1. So it will drop down to 0 voltage. Then it will be continued to 0 till 1. At 7th position it is 1, at 9th position also it is 1. So it will continue to 1. In the same manner, we'll continue with the even bit also. Even bits are 2, 4, 6, 8, and 10. So second is 0, fourth is 0, sixth is 0. So till 6th it will be 0. 8th is 1. So it will be 1 over here. There is a mistake over here. It will be 0 will be from first position to the 7th position. Then it will take a lead of 1 volt amplitude or plus VC at the 8th position. At 8th position, it is 1, 10th position it 1, then it will continue to the 1 amplitude. This is the carrier signal we have given. This is cos signal, this is the sine signal. These two signals we'll give to the even and the odd signals. So the odd signal is multiplied by cos carrier signal. So odd signal is this. We multiply this with the cos signal. So it will follow the carrier signal till this position. So till this position, it will follow the carrier signal. As it has become 0, so it will shift by a 90 degree. Then again it has 1, so it will follow from here, it will follow the carrier signal again, as it is 1 throughout. Then coming to the even portion, even is multiplied with the sine. So this is our even, it is multiplied by sine. As it is 0 till here, it will follow the sine wave. It is following the sine wave till here. There is a bit the change in there. It will follow till here, till 8th position it will follow, and then there will be a phase shift from here, not from here. There will be a phase shift from here. Okay, students, then these two signals are then added, odd and the even. ST is equals to S0 plus SET. So here there is a phase shift, so it will follow the cos signal. It will follow till here. As there is a phase shift of 180 degree, it will change and it will follow till here. As there is again a phase shift in the odd signal, it will follow, and at this position it will again change and it will continue till last end of the. So this is how QPSK signal is divided into 4 portions. Whenever you are asked for the question to draw a waveform of a given sequence, generally it is asked to draw the sequence is given, and then you are asked to draw the waveforms of ASK, PSK, QPSK signals. Then for ASK and PSK and FSK, it is simple to draw only a one carrier signal. And for QPSK, you have to draw all these diagrams, all these waveforms in your uh, exam. You have to write all these waveforms in your exam, and the final output will also be shown as this only after dividing the variations in this form. Okay, students. So this is the basically the modulator portion. Sorry. It is also very simple. It consists of a serial to parallel converter followed by a balanced modulator, and then it is added. So how it works, as I have discussed in the waveform, it will follow in the same manner. The input is a data stream of binary digits having a bit sequence of 1 and 0. This data stream is applied to a bipolar non-return to 0 encoder, which is basically this. It is followed by a conversion into two separate bit streams, that is I and Q channels, PI and PQ channels, followed by an alternate bits at the rate of some FB or FB by 2. Then frequency will be divided into 2. QPSK is characterized by two parts of the baseband signal, the in phase, that is PI phase, and the quadrature signal, that is the Q signal. One bit is directed to the I channel and the other is directed to the Q channel. The in phase signal modulates the carrier signal cos 2 pi FCT, and the quadrature signal modulates the pi by 2 shifted carrier signal, that is sin 2 pi FCT. The output of the balanced modulators V1 and VQ are then basically the BPSK signals that are linearly added in the summer, and the output is generated. QPSK output is generated in this form. Coming to the demodulator circuit, it will consist of the balanced modulators. These are the balanced modulators. This is the pi by 2 phase shifter. This is the carrier which is generated through a local oscillator. This is the low pass filter followed by an integrator. And then these are added in a mux, or a parallel to serial converter is there for serial transmission of the original masses signal. The power splitter. So this is the power splitter is over here, divides the input received signal into in phase and quadrature phase, PSK I and PSK Q. So I and Q correlators and the carrier recovery circuit. The carrier recovery circuit may be of squaring loop type. It produces the original transmitted carrier signal, which must be in the frequency as well as phase coherence. The coherent carrier signals recovered in the carrier recovery circuit are applied to the two synchronous correlators, each comprising of a balanced modulator and an integrator. The integrated circuit integrates the signals over 2-bit intervals. The output of the correlators are applied to the bit combining a mux multiplexer. Parallel I and Q data channels are converted to detected binary output data. This is how the original signal is recovered from a QPSK signal. Coming to the advantages, the bandwidth required by QPSK is 1/2 that of BPSK for the same bit adder rate. The transmission data rate in QPSK is higher because of reduced bandwidth. The variations in QPSK signal amplitude is not much. Hence, carrier power almost remains the constant. This is all about analog and digital communication lecture series. This is our last lecture series. I have covered almost all the topics or related to the subjects, related to the topic subjects which I am teaching. And if you have any queries, please let me know. And all the links for the previous lectures will be in the comment box. I'll update all the lectures. You can go through all. If you have any problems, let me know. Work hard, read thoroughly all the topics, and please make waveforms and circuit diagrams for all the topics. Until and unless diagrams and circuit diagrams and the waveforms are not drawn, the topic is not covered. You can write through the circuit diagrams, learn the circuit diagrams very thoroughly, and their operation is very easy as each block is described in each point. Thank you. Sage Anandam. All the best for you. all the very, very best students. Thank you.